We're going to talk about models of the atom. Now, we're going to kind of take a step back from a macroscopic world we've been looking at all year in mechanics specifically, and then we're going to take a look at more fundamental basics. We're going to go into more of like the history of the atom, how it was developed, why it was developed, stuff that you probably didn't learn as much of in physical science and chemistry, more as you just learned about the atom. And then we're going to take this into the next chapter, which is actually, we're going to jump to chapter 25 after this section. We're going to go to 25.1 and then 25.3. Okay? Those are both topics on nuclear fusion, nuclear fission, nuclear power in general, radiation, isotopes, all that kind of stuff. After that, we're going to go back to chapter 9 to look at fluid mechanics. All right? At that point, we'll probably stop there, maybe do a few days of fun experiments, and then have some final review time. Yeah. All right? The egg drop is not set for a date yet, but the due date is May 12th? Yeah. 12th? So I highly recommend you start getting some work done over the break. Okay? Make some prototypes, practice, crack some eggs, or don't crack some eggs. Bake. Preferably. All right. Anyway, objectives. First, we're going to talk about the different models. We're going to talk about something called absorption spectrums. And then we're going to talk about Bohr's model and the absorption or atomic spectra. The old original models, the first models that were thought of, were just tiny, solid, indestructible spheres. The atom was thought of to be the most fundamental building block that existed. The idea of protons, electrons, all that didn't even come about. Now, the small indestructible sphere theory, okay, was quickly eradicated or gotten rid of once the ideas of charge, okay, and the electrical nature of an atom came about. So once they realized that atoms could conduct electricity, then things started changing. People started realizing, okay, it can't just be this like this little nucleus or this little hard element that sits there as a sphere. It's got to be made up of different parts. So that's where we started coming up with the idea that it's going to be made up of electrons, protons, neutrons. All right. So the first model that's really important is the model in 1897. And this was the idea that the electrons are embedded in the sphere itself. Okay? They are embedded in a spherical volume of positive charge. So the red is like this positive big sphere. And then suddenly there's all these little negative charges in different spots. Those are all the blue spots. When you were younger, you probably heard plum pudding model, which nobody knows what plum pudding is anymore, so it's a terrible analogy. Did he teach you plum pudding? Yeah. Which is fine. But anybody know what plum pudding is, honestly?
I don't know. What's plum pudding made of plum?
It's pudding, but it's got like raisins in it all over the place. So think of it this way, it's like a bowl of pudding with different like raisins in it. Those are the raisins, right? An easier way to think about it is a watermelon that has seeds. Okay, a watermelon with seeds. The seeds are like the electrons. The watermelon is like the big positive charge. That could be an analogy to the Thomson model. Another one somebody in the other class said was like a muffin that has chocolate chips throughout the whole muffin. The chocolate chips are all the electrons. The muffin itself is the giant positive sphere. Okay, there's many analogies, but plum pudding is the traditional way to say it. But I mean, plum pudding hasn't been around for a long time, so most people don't even know what plum pudding is. Like my parents ate plum pudding. It was really when they were kids, not recently. Yeah, so this was thought of. This was thought of as only as only electrons, and then one big positive sphere. No protons or neutrons or anything. Now again, this came about because of the result of the electrical nature of the atom. That's for the idea of, all right, you know what? If the atom is electrically charged or can conduct electricity, it's got to have these electrons somewhere. So they threw the electrons into the model. That's the only big difference between this and the previous model. Okay? Let's go to the Rutherford model. The Rutherford model, which is about 24 years later, right? No, 14 years. Right. Side note, something good to know. Although we say Rutherford model and Thomson model and Bohr model, a lot of the time those scientists are credited for it, but sometimes they don't actually come up with the ideas or discoveries themselves, whereas somebody that may work under them does. So when you work as a TA in college for somebody that's doing research, a doctor that's doing research, and you're their TA, and you're doing all this data analysis, you come up with this idea. right?
But you don't get credits.
You don't always get credit. A lot of times you don't get credit because you're doing research for them. It's their idea of the research, and you're just making the conclusions. Although your conclusion may be the one thing that they take from all the research, it goes under the doctor's name or the person's name you're studying for, not under you. A lot of people, though, nowadays, because the world is more respectable and it's easier to actually track who did it, do give credit where due. So they'll say it's a paper by so-and-so, and they'll list the people that worked on it with them, or they'll give some sort of credit or some sort of, whatever, awards to those people that did it, not an actual word, but words in the sense of that was your accomplishment online. But at this point, or this day and age, okay, the scientists themselves would take credit for anything that was done by their students, especially. Same thing with guys like Pythagoras and stuff. A lot of the theories are their own. Okay, there's a good amount of work that they don't actually do themselves. Okay. Now, the Rutherford model was the idea where the electrons orbit the positively charged central mass, which we then start calling a nucleus. Okay, in a manner similar to planets orbiting the sun. Now, this came as a result of what experiment? Does anybody remember what experiment it was that came as a result of?
Gold sheet.
Yeah, the gold foil experiment. Can you grab a desk for me, Mike?
Mass.
Mike's going to pull the desk down, okay? I emailed you saying I wasn't on gym duty. That was tomorrow. I messed up the face. Sorry, yeah, just take your time and then I'll give you the difference in time after, okay? Here, Joe. Is it nobody in it? Is there a class? Oh, okay. Great, Mike. Appreciate that. How many minutes into the period are we? Right, it started at 15 and it's 30, so 14 minutes. That's 14 minutes back. 19 minutes. Okay, so the Rutherford model, again at the central nucleus, came about, as Mike said, as the gold foil experiment. What is the gold foil experiment?
They shot protons through a thin sheet of gold foil, and they saw that most of the time the protons would pass through, but sometimes they would bounce back, so we realized there had to be something repulsing the protons,
Which was the?
which was the protons of the atoms in the gold foil.
Yeah, the nucleus of the atoms. Very good. So the idea is this. If I'm able to imagine there's like, anybody been to batting cages before? Batting cages, the nets are just the drop nets, they hang, and the net holes are like this big, because a baseball won't fit through that hole. Okay? But if I took golf balls and threw golf balls at the net in a batting cage, most of them would go through. Some of them might catch part of the net and fall, right? But wouldn't most of them fit through the holes because the holes are made for baseballs? Golf balls are tiny, they'll go through easily. Or take literally peas in a pod, and take them and sit there and throw them at a net. A lot of them would go through the net if it was a thickness like a batting cage net, but some of them might hit the net and fall down. That's exactly analogous to the experiment. The experiment, though, was that protons were sent. Most of them passed through, which said that most of the atom is made up of empty space. But then, some of them did get reflected by that positively charged nucleus. Okay? That's why it was a proton that was fired at the actual gold foil. Okay? Let's see. Another thing that this told us was that as a result, if there's a positive nucleus, and it's all positive, and then there's some other negative part of the nucleus, or another negative part of the atom itself is considered to be unstable. Okay? The atom can be broken up. That's what this came about. Whereas prior to this, with the Thomson model, with the electrons embedded into that positive sphere, it was thought of that the electrons could not be removed. They couldn't be pulled out of there because they were part of the positive sphere. Whereas here now, we can see that these electrons could go off into orbit or get pulled off into space. And as a result, the atom itself could be considered to be unstable. So before this, it was thought that all atoms were stable elements and they were neutrally charged. A bunch of positive in the sphere and a bunch of negative little seeds from a watermelon. Okay, but now we can see that it is not. Now, between this model and the Bohr model, a huge revelation came about. And it was called the atomic spectrum. Okay? Now, the way this works is as follows. Ever go to a store and in the storefront there's an open or close sign and it's like a neon light?
Yeah.
Isn't that neon light in like a little tube?
Yeah.
Okay, what's happening is there's a gas in the tube. Neon, the gas actually, one of the noble gases on the, what is it, the last column.
Yeah.
I forget what family that is, the 17th or 18th or something. So that last column on the periodic table, those noble gases, neon is one of them. When you go to a store, there's neon gas in there. And what happens is this. When you apply a voltage to an atomic gas, it gives off a certain color. And that's what you're seeing in the top here. 3 different atomic gases in different tubes with voltages, and you'll see that the colors come off. Now, the color of that light can then be passed through a prism. Look at the bottom diagram down here now. Could then be passed through a prism. So the light shines through a single slit, then it hits a prism. The prism breaks up that light into the different possible colors of its spectrum. And what you get as a result is like a atomic spectrum profile. So this first one here in the middle is hydrogen. And what you'll see for hydrogen is there's a spectrum line here, 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 and here. That's it. But then when you get to mercury, you see all these different spectrum lines. When you get to helium, you see all these spectrum lines. It turns out that every element has a unique spectrum, like a fingerprint. So this enables us to identify the possible elements that exist. Now, this was also part of the reason we came up with the element for helium. When the solar spectrum was discovered, the spectrum itself was completely different from any spectrum that had existed. And they came up with this idea that, okay, there must be another element that is not on Earth naturally occurring, but it does occur in the sun, and the sun is made up of helium gas. Helium hydrogen, really. But a lot of helium gas. And they gave the idea of helios, that's where it came from, but it was discovered from this idea of atomic spectrum, along with many, many of the elements that weren't around in that day, or weren't known in that day. Anybody know, how many elements are there known to man right now? Is that what it is? I thought it was like higher than that.
5.
In the other class we have the elemental table, but we don't have it here.
Why don't we just look it up online?
Let's look it up online, Ev. That's a great idea. Why don't we just do that?
It's 5.
But that's sarcastic.
No, I'm doing it right now.
Okay. Look up guy gets kicked in the face by a train.
92 that occurred
Can I run a search on here? Periodic table?
I'm still going with 5.
I gotta run Google, I guess.
118.
What is it?
118.
You already looked it up?
Yeah.
Awesome. So 118 elements.
Right.
I don't have to actually check. You're not like joking,
I
right?
was right, 118.
Awesome.
5.
This is what's good.
5? I don't think it's 5. No.
I'm
I'm
almost.
gonna go ahead and say, don't think it's 5.
I'm almost 95% sure that's 5.
So 118 elements. Now, before this idea of the atomic spectrum around, many fewer elements were discovered. It does not mean that the material needs to be a naturally occurring gas. Like, don't assume that only if it's a gas you can test it. So they can take a solid, make an atomic gas out of that solid, and then run it through one of these tests as well. So things like, for example, mercury, that's a naturally occurring liquid, okay, at room temperature, mercury. Whereas other ones are naturally occurring solids. Let's see.
5.
This is used so often, and I explain it all the time, but people don't seem to understand it because I guess they weren't paying attention in physics. But in forensic science, this idea is used so often, it's unbelievable. So if they have like a mixture of something at a crime scene, they want to know if there's blood in it, or if they want to know there's certain amounts of colors of paint and pigments, or if they want to know there's a certain concentration of an amount of some sort of element. This idea of atomic spectra is used all the time on a much more complex level than just this stuff.
The UV light?
Okay? It's able to take the material and pretty much send light rays or electromagnetic rays into it and see what you get out as a result. And as a result, you can see what the chemical makeup is of that material.
I think I saw that, like they try to bleach the blood one time.
You get to me
And like they
100%
just
steel.
and it
Steel, limestone,
And they're still able to see what was left behind.
Yeah.
That's an application of this, yeah. Fluorescence, that's what that is there. All right, let's go to the next.
And limestone.
So the Bohr model,
Limestone.
The Bohr model came about after the idea of atomic spectra, and as a result of the idea that each of those atomic spectra have specific increments of wavelengths or lines on their spectrum. So like when we looked at maybe the hydrogen one, I don't remember which one it was. Say this was the atomic spectra of one of the elements. This spectra will not occur anywhere else for any other element. And as a result of that theory, Bohr came up with the idea that electrons have to jump from one orbit to another. From one orbit to another. Okay? And they're not going to end up in between orbits. Remember how you learned about the orbits of electrons? 2, 8, 8, 2 as the main 4. And then you go on further, there's like P and S and all the different elements in the orbits. The shells. No. The idea though is that the electron cannot jump from one shell to the next or end up in between. It has to end up right on that shell. So there's a quantized or a specific amount of energy that enables that electron to jump. And that came about from this experiment. Okay, because these colors come about as a result of electrons moving. When an electron is excited and at a higher orbital level, and it comes back down to its ground state, it has to give off energy. Okay, it lowers its energy level. Where does the energy go? It gives it off in the form of light. That amount, that specific amount of energy, corresponds to one of these colors on the spectrum.
We did a lot.
Okay? You did a lab last year on this?
Yeah.
So you have an idea of what I'm saying then?
Yeah.
All right. Now, the other idea is this. Here's the nucleus. Here's, say, the first 2 electrons. Here's the second shell. Okay, let's say that this electron, well, let's say there's a few in the second shell also. So let's say that this electron jumps up. Okay? It gains energy. It absorbs energy. So you hit it with some radiation, it absorbs energy, it gets excited. This electron now ends up on the outer shell. But it doesn't want to stay there. It wants to be stable. Just like you want to be stable, you don't realize it. Why do you fall to the ground when you step off of something? Because gravity pulls you down. You want to be at 0 energy level. Remember how we talked about potential energy? And right now I have potential energy relative to the ground. So if I walk out the window, what would happen?
You have a lot of
I would probably die, but I would fall, right, generally? If I step off of a step, I fall to the next step. You're falling to a stable environment every time you take a step. An object's tendency is to go to a stable environment. Same thing with an electron. It wants to go back down to that lower level. But when it does, all that energy it absorbed when jumping up has to go somewhere. So it jumps back down, okay, and it emits some sort of energy. And we'll talk about that energy in a moment. But it gives off a certain amount. And it's a quick amount of energy. It's usually some form of light or radiation. Okay, but it's not like a continual, it's not like a light bulb is going to stay lit. This would happen, you would see like a flash. That's what you would see. Okay? All right, now, the last part of this is you can determine the frequency of this radiation. The radiation that's emitted right here can be determined using what's called Planck's equation. Let's talk about this guy Planck, who's really, really important to science. Amazing discoveries. Here's Planck's equation. He what?
Cool monocle.
He has a cool monocle, does he? Did you look at his picture?
Yeah, I'm pretty sure last year. I think I remember from last year, like a pretty Pippin monocle.
I'm glad to hear that. Pippin monocle.
I'll confirm or deny it.
So,
Yeah, I'll let you know.
You got
His
all
glasses
the
looks-
levels.
maybe, well, it's possible he had glasses and a monocle. Maybe he had it in one picture.
Scroll up a little bit.
It might have been Tesla with the monocle, Nick. Check Tesla out. I think he had a monocle.
He was a
I have monocle.
Do you?
Can you scroll up a little bit? Like your dad, how many?
Is that good?
Yeah, he looks like someone that.
All right, so take a look at the equation.
My dad's hot.
What has capital E stood for all year? Guys, come on, focus.
Energy.
Energy. E, capital E has always been energy.
So little e is what?
Little e was, or the elementary charge, remember? 1.6 times 10 to the negative 19. Okay? So, energy equals H, which is called Planck's constant. It'll be on the bottom of your formula sheet. It already is. This is a known value. Planck's constant is 6.63 times 10 to the negative 34th joules seconds. Not joules per second, but joules seconds.
What's the difference?
Okay? The units are multiplied, not divided. Like
Yeah,
meters
but
per
what's-
second.
What's the difference between like this, like not like the conceptual, like the actual difference? Like,
It means that to come up with this answer, you took a unit of joules and multiplied by seconds to get it. You'll see the units.
Which one's faster?
It doesn't work that way.
No, it doesn't work that way.
This is not a rate. Joules per second is a rate of change. This is not. This is a product of two values. It's technically an integral, but that's a calculus term.
Isn't a mole the same?
Is a mole units of joule seconds?
Well, not the units are different. Mole is mole.
I want to chop it up.
You may use Planck's constant when you're calculating molar mass and stuff, maybe. Maybe the negative 34 is where you're thinking of. Isn't Avogadro's number something like that? Or,
Yeah.
but I don't know if it's negative 34. Maybe it is. I don't know. Check it out. What is W? Oh, it's not W. Wow.
Omega.
Thank you. What does omega stand for?
Swag.
Stop, Mike. What does omega stand for? Come on. We did this earlier in the year. We already looked at omega.
One of the letters.
It is a letter.
It's Greek.
It's Greek.
Was that your fraternity? Welcome, Greek. Chi Omega.
What does it stand for? Come on, nobody? Really? All right, frequency.
Oh my
Frequency.
goodness.
Remember frequency and wavelength?
This is embarrassing.
Lambda was wavelength, omega was frequency. The units of frequency are hertz. Hz. Now, what were hertz really? What is a hertz made up of? What do the units of hertz really mean?
Seconds per second.
Cycles, or 1 over seconds, or cycles per second. So look at your units. Ready? Units of energy are always what? Or usually what? Potential and kinetic energy are measured in?
Joules.
Joules, thank you. Planck's constant is joules times seconds, and hertz are really cycles per second, or 1 over second. So what happens? Seconds, leaving behind, joules equal joules. All right?
Why is it Jules?
Energy is measured in joules. Energy is measured in joules. This is just to check your units out. That's all we're doing here, to make sure they work.
Dividing by them, would the seconds still cancel out?
Yeah, so if you were solving for something, you would divide by the other quantity and you'd have to cancel still. We'll do that in a minute in an example. Okay? All right, let's go on to the next. All right, quickly. A photon is 1 unit or quantum of light energy. Okay, 1 unit. Oh, what time is the period over?
55.
Oh, 55. Okay. We're good. Thought it was 49. So a photon is a unit of light energy. So this is what we're talking about. Follow the cursor on the board. Photon comes in, hits the electron. It gives the electron energy. The electron absorbs that energy. It jumps up to the next state. But now it wants to go from that state back down to the ground level. When it gets back down to ground level, it emits energy in the form of some radiation. In this case, a photon also. Okay, this is called spontaneous emission. All right? When light of continuous spectrum shines on an atom, an electron can jump to a higher energy level. It will then come back down. It'll then come back down. Now, have you heard of the Northern Lights before? Have you seen them? Yeah. Aurora Borealis or whatever you say? Yeah. Do anyone know the correlation I'm making to this right now?
So like when radiation from the sun hits the atoms in the atmosphere, like on molecules in the atmosphere, and then the electrons get go to a higher state and emit a different color light.
When they return back to the ground state.
They emit different light.
Yeah, do you know why they get trapped? You're absolutely right, except for the why part.
Weather.
Why do photons from the sun, it's photons, you said radiation, photons, same thing. Why do photons from the sun get trapped around the northern pole?
Earth's magnetic field.
Yeah, that Earth magnetic field, remember that comes out of the poles, right? Like this? And those magnetic field lines are very close at the poles. It's a strong field at the poles. So the photons get trapped in the air. They interact with the gases in the air. In the air, there's argon, there's neon, there's helium, there's hydrogen, there's other compounds like methane, which is a compound of gases and other things. But there's a lot of things that make up the air around you. So all of those colors are the interactions between the photons and those atoms of gas in the air. Those are the different shades of colors you're seeing. So this idea is completely responsible for the northern lights. Okay, that's where they come from. Just a small application of it, okay? With an example that might take us a little while to get through. Can I get a reader, please? Nice and loud. Thomas, go ahead.
A photon in mercury atom drops from energy level 4, 5.43 eV.
And this should say electron. I don't know why I wrote photon. Sorry. I just realized that now.
So electron,
Continue.
Energy level 2, 4.66 eV. If 1 eV is equivalent to 1.6 times 10 to the negative 19 joule, then they're telling the frequency of the electron.
Thank you. Oh no.
Or no.
This one will be photon. So the photon is emitted afterward once the electron drops back down. But the first part should have said electron. Okay. Anybody know, ever hear EV? EV?
Something wrong with us,
That's me.
yeah, charging.
Is it, valence electrons?
Yeah.
Ev.
Volts.
Something with volts.
Ev.
EV.
Yeah, that's me.
It's true. EV.
Electric electron volts.
Energy
Electromagnetic
volts. Sorry.
Zeus.
You're close, EV. Electron volts. Electron volts. Okay.
Well, that's not really a question.
Well, I'm just saying, have you ever heard of the term before?
Okay, okay.
So volts are a unit of power, right? Voltage, power. Electron volts are a unit of energy. Okay, and 1 electron volt in energy is equivalent to, that many joules. Notice that number, isn't it familiar?
Yeah, it's Q.
Yeah, it's the Q for a proton or an electron, but it's in units of coulombs there, isn't it? Remember, Q for a proton is 1.6 times 10 to the negative 19 coulombs, not joules. But the relationship is there for a reason, okay?
So I mean like different words then, it's the same thing.
But it's not. Look at the units. It says joules. That's what I'm saying. If it said coulombs here, this would be 1 E is equivalent to that. Remember, the fundamental constant E is equal to this number with coulombs. This is an electron volt, okay? Now, we know that it's starting at level 4 and is dropping back down to level 2. So it must have gotten excited at some point, right? It must have gotten a gain of energy in order for it to raise up to a higher energy level. So here's the rings. Here's this. Let's say that's the nucleus. Ring 1, ring 2, ring 3, ring 4. So it was at, I'm guessing, level 2 originally. It got bumped up to level 4 up here. It then wants to drop back down to level 2. We put it in blue so we don't confuse it with the nucleus. See, the electron was on level 2 at some point. It got hopped up to level 4 on energy. It then came back down to level 2 and emitted a certain amount of energy. We want to know what kind of frequency was emitted. What kind of frequency was emitted? Okay, what I should really say, radiation. Because I'm assuming it's a photon if it's visible light. But we'll just say radiation for now. But a photon does work in that sense. But don't get confused by it. Because it doesn't turn out to be visible light. If the electron drops back down, it loses energy. It loses energy, gives it off. So look at the energy levels at 4 and 2. What can we figure out from the two of those? What might be useful in this kind of a problem to know? We know the energy level at level 4. We know the energy level at level 2. What should we find?
3.
Not 3.
1.5.
The difference.
What, Mike?
6.
The difference.
The difference. Why the difference, Mike?
Centigrade.
Okay. Nick?
It's gonna emit the change in energy to get back to the, level 2.
Yeah. It's got to give off that energy. So the difference is exactly what you're calculating. That's what it's giving off. That's big E in this problem. All right? So the difference in the energy levels is the amount of energy it has to dissipate or give off. That's capital E. H is known. What are we trying to find?
Omega.
Yeah, the frequency. It says determine the frequency right here, right? Determine the frequency. So we're finding omega. So E over H equals omega. Here's the problem now, though. We cannot have E in electron volts. A moment ago we showed that this is joules times second, and this is 1 over second. So we have to convert that. But I'm not going to convert twice. Let's find the difference, and then we'll convert that answer. So find the difference between 5.43 and 4.66. $0.77?
Yeah. Exactly.
3.4 and 4.3 added together is 7.7. Just check to make sure. This is units of electron volts. That is not what we want. We want joules. If I know I start with 0.77 electron volts, and I want to get rid of electron volts, what do I put on the top of the fraction? And what do I put in the bottom of the fraction? What goes where? Dimensional analysis.
Oh, I hated this.
Yeah.
This is the hardest thing we did.
Yeah.
Come on, you want to get rid of something that's in the top, put it in the... If you want to get to joules, put it in the... Okay, now, what was the conversion, the problem? You were told.
1.6 times 10 to the negative 19
Over 1, good. So 1.6 times 10 to the negative 19 joules is really equivalent to 1 electron volt. Electron volts cancel. We multiply those two quantities together. Okay, I think it was like 1.23. Somebody check. I don't have the number in front of me. Is that right? Yes? 1.23 times 10 to the negative 19 joules. That's how much energy, a very small amount of energy, because we're looking at one single electron in motion. All right? A small amount of energy. That is going to go in up here for energy.
Is there a certain number like an electron can't exceed? Like, is there like
It depends on the orbital state. It's going from where to where. If it's going from like an orbital state of like level 8 where it's got a lot of energy and level 1 low energy, you can get a lot more energy out of it. Is there like a number that just can never go bigger than? I'm guessing the biggest element that exists from its highest energy level to its ground state would be the maximum. But I don't know off the top of my head now. H is Planck's constant. Plug it in. Okay, so we end up getting, let's look at our fraction. It's going to be this number, 1.23 times 10 to the negative 19 joules over Planck's constant, 663, 10 to the negative 34, joules times seconds. What happens to joules, people? What are you left with now?
Seconds.
Not seconds, be careful.
1 over 6.
1 over seconds. What are the units up top?
That's tricky.
If there's no units, you just say 1. There are no units. So it's 1 over seconds. And 1 over seconds is what hertz are. And we're looking for frequency. You get, listen, 1.8 times 10 to the 14 hertz. This happens to be infrared radiation. If you look back at your spectrum. Remember, over the weekend, make sure here, on the board, right there, right now. It will be on Moodle, but just in case.